could get out of here, really. All right, Gordon asked us to start with saying something about how we got into this hobby. I started off as a kid. I used to like taking apart televisions and making radios and things. 1956, 7, I made my first RC radio for playing. Couldn't afford to buy one, so I had to make them. And that didn't work very well. I don't think I ever got a successful flight with that first radio. Pike radio it was called. And then I found this thing called an aerotone receiver, which is about 3 inches long and 1 inch wide. Made that up, had a tube on it and 2 transistors, newfangled. And that flew extremely well, and based on that I made several radio-controlled airplanes, and some of them even flew. And the smallest one was, I had a fascination with making small things for some reason, I don't know. But made a microplane, 20 inches wingspan. And that was shoulder wing, stick and tissue. And that flew extremely well. It was a 1-channel radio with a glow engine. And then in about 1959, I guess, I discovered girls and gave up this aero modeling stuff, and got in a rock band and did all that kind of stuff. But that fascination with mechanical things has gone, or things that work, engineering things, has gone with me through my career. I got a couple of degrees in mechanical engineering. I got a PhD then in computer science, because I found out with programming you could build even more complex things that work in a different space. And then through my career I went to Xerox PARC and wound up in the Bay Area. When you're in the Bay Area or in technology, what do? You start a company, right? So I was involved in 2 startup companies, one of which was a CAD company, doing mechanical CAD. And again, that factored into this hobby. And then, well, anything else of relevance there? I don't think so. Holy cow. Sorry, something just flew by. Yeah, so then I retired, I don't know, 15 years ago and got back into this game again. And all these pieces of electronics, computer programming, mechanical engineering, modeling, CAD systems, it all sort of comes together and all factors into this sport, which is why I do it. And one piece that was kind of missing, sort of, was, yeah, I could design things in 3D CAD, but to make them, it was a bit of a pain. And so, in some ways, my talk will be an extension of Gordon's talk. It's what 3D printers have meant to me and what I've done with them just recently, and enabled things that before I couldn't have done. So there's 4 things I'd like to talk about that I've done in the last couple of years. The magic thing about 3D printing, is this. Go back to when I was doing this stuff years ago. I just would never have believed it. Sounds like something out of Star Trek. Design something in a 3D CAD system, and with a very few steps, pressing a couple of buttons and wait a while, and bingo, there's the 3D part. And it's kind of taken for granted now, but it's still kind of magical to me when I see this thing come out of the printer that I had on the screen, and it looks the same, usually. So anyway, so for me that's been a big enabler in the last couple of years, and to give a bit of a new impetus to getting back to do some different things. The first thing I want to talk about is, why did we get into these 3D printers? I've been thinking about 3D printers for some years, but I couldn't come up with an excuse to buy one. I thought, if I don't buy a 3D printer, I'll print a couple of figurines and things, and then I'll sit on the shelf. But then Charles Monnion in France, as Gordon mentioned, he came up with this design for a half-gram servo, which a hobbyist couldn't think of making by themselves. You can't cut those gears that small and all the rest of it. So Gordon got onto this, and he contacted a bunch of us and said, "Hey guys, how about we make these things? We could all get printers and work on this." And, yeah, sure. Order a printer. $250 or something. And we got Charles's design, and when I got a hold of Charles's design, I printed up a few of the parts and sort of assembled it a bit, and I didn't like a number of things about Charles' design. I mean, it was a great leap forward for me, and it sort of set the stage of what could be done, but I could see a whole bunch of things in it that I didn't really like. And one of the big ones was the gears on it, done with a standard gear design program. And the problem, I don't know if this is universally the case, but with gear design programs for these tiny gears, is they seem to design them to the nominal size, so that the gears would mesh perfectly. You know, they don't seem to do a lot, I don't know if I got this right, about clearances, and the way the clearances are done. And funny, so what people do is they make they design and build the gears, and then to get some clearance, they move the shafts apart a bit. And there's, you know, rules of thumb for doing that. And that's just the wrong way to do it. So I decided I'd write my own gear design program. So I got right.
Ladies and gentlemen, for the nostalgia contest today, I only need the new airplanes. Any airplanes that had not come down yesterday to be judged, to be brought down at noontime.
I'm gonna go over there with wire cutters and cut the wire to the speaker.
It's we need a chair. Wants to bring their other airplanes back down and display them, that's fine. But they do not need to be judged again.
So when gears mesh, you know, the one gear is coming in the top of the other gear. So if you take the design of all of the counterclockwise faces and just move that design around a bit, you create clearance, and you don't change the behavior of the gear at all. So by doing that, and another thing about Charles gears, you have no undercuts on the gears. You put that in, you can get much higher gear ratios. You can get pinions down to 7 teeth, and with that I could reduce the number of stages in the gear from 3 stages down to 2, with the same overall gear ratio of 140 to 1. So with the same gear, 1 fewer gears. Another thing about the way gears went together, the Hall sensor, there's a magnet on the output shaft which is near a Hall sensor. I think we talked about Hall sensors.
You can talk about them. People may not know.
Okay, the Hall sensor detects the strength, this will be relevant for later in the talk, so it's worth mentioning. Detects the strength of a magnetic field perpendicular to its surface. So if you put a magnet on a shaft and a Hall sensor nearby, as the magnet rotates, the magnetic field going through that Hall sensor will maybe start off the north pole pointing that way, and as you come around, no field, you know, going through the Hall sensor, and as you come around 180 degrees, the field's going the other way. And the Hall sensor can pick that up and put out a voltage which is proportional to the strength of the magnetic field hitting the surface perpendicular. So on Charles's design, he had a magnet sticking out the bottom of the shaft with a Hall sensor mounted there. They're little tiny things, you know, 3 millimeters square, that sort of thing. This made it very difficult to mount the servo because it's no flat surface. So I wanted to fix that. So I put my Hall servo sensor sticking upwards instead and integrated the magnet with the gears. So now it's got a flat surface to mount on. And the final thing was the software. And this is a problem, I think, with all servo software. That you buy the servo and it's set up to give you the full throw for some range of the input PPM signal. The way servos are driven, just briefly, for those of you, I'm sure you guys know this, there's a string of pulses come in, separated by nominally 20 milliseconds, and each pulse is between 1 and 2 milliseconds wide. So it goes high for 1 to 2 milliseconds, it goes low, 20 milliseconds, and then another one. And the width of that pulse carries the information about what position you want the servo. So 1.5 milliseconds, you want it in the middle. 1 millisecond full one way, 2 milliseconds the other way. People have different amounts of timing, and some transmitters, or receivers, I'm sorry, put out different amounts for full throw. So I wanted to put into the software a way I could calibrate this, and so I did that. So with my servo, you can take the servo, attach it to your particular transmitter and receiver, fire it up, and then calibrate it so it will do exactly the throw that you want for the full range on that receiver with that transmitter. Which seems good. And the other thing was for micro stuff, the weight of the wires running around the plane can be a consideration. And with servos, as you know, you've got 3 wires that go power, ground, and the signal. Now, power you can daisy chain, so you can take power and ground to one servo and then to another, if you've got, like ailerons or several servos. But still, the signal has to come out individually. Well, there's another form of signal which is called CPPM, composite PPM, which puts all the signals onto one wire. There's other protocols for this, but that's one of them. And all the pulses are mashed together in sequence on the one wire. So you can take that wire, run it around the servos, daisy chains. You don't have to have all these wires and plugs coming back to the receiver. So the one that I did with the software in it can take that signal as well if you wanted to. And so you can run CPPM to this servo. Excuse me a second. Right, so yeah, I put that together and made a servo. Here there's a little plane, test plane for trying them out. There's the servo. It does weigh 0.5 gram. Oh, I ought to mention Nick Lecty. Of course, Nick Lecty has been selling 0.5 gram and 400 milligram servos for some years now. And just like all of Nick's stuff, if I was to build these and sell them, they cost 5 times, 10 times as much. I don't know how Nick does it for the people say, oh, Nick servos are kind of expensive. They're beautifully made, they work beautifully, and how he sells them so cheap, I don't know. It's crazy. But anyway, by the way, this all my radios are the Rabbit hip hop radio that I developed. I didn't like the Plantraco stuff because you had frequency conflicts, so I developed this frequency hopping spread spectrum version of the receiver, then developed my own receiver, the Rabbit receiver, and Nick sells those. They weigh down to 100 milligrams for the 8-channel receiver. You can either have servos or actuator outputs, so there's that. And the versions I use, I've got gyros on them, so this thing's got 6-axis gyro in it, and there's the receiver. But anyway, that's not what we're here to talk about. So just to show it really does work, see, there's a rudder and there's an elevator. See? Real servo. 0.5 gram each. And one comment about anybody who wants to make these things. I found that making these things on this little tiny circuit board, you put the surface mount components on and heat gun them and they stick down, but then something doesn't work, you didn't get a good contact. So you've got to unsolder them, or you plug them into a test rig and then pieces fall off. So I just thought I'd pass on. The way I do this now is I make the servo, this is a servo, on an extended board. Let me show you. So there's these big contacts sticking out the top there, much bigger than the normal contact. There's a row of normal contacts on the board, but then there's this extension to the board, and that can go into this 0 insertion 4 socket with 10 contacts. It goes to a 1/10 inch spacing header, plug that into a breadboard. Now I can test that servo, get probes on it, other things I want to use to debug this thing, to get it working. If something goes wrong, all I've got to do is take it out of here. I can then go solder whatever I want, plug it back in and go on. And that's how I make my receivers as well. And it makes it so much easier.
And then you cut that off.
And then you cut that off with a pair of scissors. Right. Yeah, the board is 4/1000 thick flex board. Here. Turn that around. See it. The next project I want to talk about is when we talk about coming here to meet this year. There's a bunch of us that don't come every year. We're going to do it again this year after 5 years. Nick said, "Hey, let's all build the same plane. Let's all build a plane with a common characteristic that it'll have no control surfaces, and it'll have 2 motors, which are on gimbals that go vertically. So you have a kind of an aileron effect. So, oh, that's another great project for my 3D printer. So I fire up the CAD system. I'm always looking for an excuse to use the damn thing. And I built these little, designed and printed these little gimbals on this plane here, and brought them along. So let's see if this can. Well, there's nothing particularly technologically advanced about this. Oh. So, okay, we got up and down and, oh, wrong stuff. Aileron type action, throttle, and, oh, that's the gyros. That's yaw on the two motors. There we go. Right. Stop it.
It's annoying.
That's annoying. I should have put my linear servos in here. These are rather noisy.
Is your gyro-enabled receivers, is that software switchable? Can you switch the gyro out?
Yeah. Well, the nice thing about gyros on this is I can turn the gyros on, or I can lock them, or I can put them in a third mode, where I can change the PID parameters. There's 3 PID parameters for each axis, so there's 9 PID parameters, and I can change all of those while it's flying. So
I'm sold.
it takes a bit of presence of mind to do that. What I usually do is I'll fly it. If I want to change the gyro parameters, I'll land it. And then while it's sitting there, I'll change it and then pick it up and launch it again. Because changing PID parameters while you're flying is.
Like if you sort of got nervous in the air, you might not even notice, but on the ground,
Yeah.
notice.
Yeah, that's right. So yeah, there's that one. The third project was, here's a project on this same plane I forgot to mention. A couple of years ago, the toroidal props became a thing on the web. And I thought that looks fascinating. I'd like to make one of those. So these things are claimed, I don't know, have you seen these things?
Yep.
Yeah?
They're popular on boats now.
On boats, yeah. They seem to work very well on boats. But this is the air version. And the idea of this is that, I think, is one of the problems with propellers is tip losses. So, holy cow. Sorry.
Buy that in the gym.
The other tip.
That's not micro. Get out of here.
That's the other extreme.
Yeah, that is the other extreme. The idea is that you get a lot of losses from the tips. Off the tips of propellers, you get tip vortices, and that carries away a lot of energy. And the idea of this is that it's stated, there aren't any tips. So how can you have tip losses? Well, there is a tip, but there's only one for the 2 blades. And so these so-called toroidal props were claimed to be much quieter and more efficient than the equivalent regular prop. Whether you count that as 2-bladed or 4-bladed, I'm not sure.
Is there a limitation though on the rotation of the prop because of that design? In other words, meaning can they do only 200 miles an hour versus say 600 miles an hour? Or is there a limitation on?
I don't know why there. I don't know. I don't know why there would be.
That's why.
Yeah. In the case of the marine propellers, you can see it. There's these water tunnel videos of seeing a regular prop turning at high speed, and you can see the bubbles in the vortex trails off the tips. And with the toroidal, there are no vortex trails coming off the tips, and they're much quieter. On this, people ask me, is this quieter? I think it is. I've got a prop on a what do you call it? Timber, small timber airplane, much bigger than this, and that with a regular prop has this whine, high-pitched whine. With the toroidal prop, the whine's gone. But as far as efficiency goes, it's very hard to tell if these are more efficient or less efficient. because, you know, it may be that the two-bladed prop I put on was a lousy match for the plane, and the toroidal was just in the sweet spot, you know, so it would appear better. So without doing a whole range of tests to optimize the prop for this motor and plane, and a whole range of props to optimize the toroidal, so I could then compare them, you know, I can't tell whether it's better or not. But in both of these cases of the Timber and this plane, I put this on and the plane flies the same. So it's no
current
noise.
draw is the same.
Sorry?
The current draw.
I've not checked that, but yeah, good point.
Maybe
Current
for
draw.
efficiency, just to, if it has the
Yeah.
same flight characteristics with the same current draw, it's probably a good match on efficiency.
Yeah, no, you're absolutely right. And the claim for the marine ones is that the efficiency is much greater. You get more range for the same speed. Yeah. On this, I don't know. I haven't really checked it.
I'm surprised we're not seeing these on you know, naval vessels where they really want to silence the props.
Yeah, I would think they would come
It's
in.
not-
Yeah.
It's really not new. If they were great, they'd be all over.
But anyway, I
It's a
thought-
little bit of
The nice
internet
thing,
hype.
nice thing about this was, you know, 3D printers came along. No way could I make one of these without a 3D printer. And so, hey, just got on the old CAD system again. Print them out.
Wait,
Fine
is
or
there
flight.
is there like a parametric design to those, or did you that looks about right at?
That looks about righted parametric design, so I can tweak some parameters and fiddle around. But yeah, it's a very simple design. Actually, it looks complicated. And there's some wrong ones on the web. There's one guy who does a very nice channel, and he's popularized these, and people have copied his designs, and he's got it wrong. He's got a tip. We don't need to go into that.
Interestingly, you might be interesting to know what the, you know, normally you might want the pitch of the following blade to be a little bit higher
Yeah.
than the leading blade because of the airflow. So there's probably a lot of very complex set of equations for that.
I bet there is. Yeah, right. So, there's that. And then the final thing was on the 3D printing was about linear servos. What am I doing on time here?
Take as much time as you want.
Ooh, okay.
Yeah,
Please.
25 minutes.
All right. Well, let's see, how to start into this. You all know what a linear servo is, I assume. There's a picture of a mini micro linear servo. And what you got is a little motor, pager motor, driving a pinion gear, which drives this larger gear. The larger gear is attached to a threaded rod that goes along. So that gives you quite a good step down. And then there's this, sorry, it's not very clear. There's this follower that sits on the threaded rod. It's stopped from rotating, so as the threaded rod spins, the follower runs up and down the threaded rod. Okay? It's very simple. It's only one gear, and they work very well, as you know. That's what's in here, commercial linear servos driving this thing. There are a couple of problems with the linear servo, well, a couple of problems with the rotary servos as well. Two things. You need to know where the output shaft is on a servo in order to know, do I have to move it to put it where it needs to be? So you've got to measure, the electronics has got to have some way of measuring the position of the output of a servo, linear or rotary. And so how do you do that? The standard way of doing that is with a potentiometer. In the case of a rotary, so that's a variable resistor. And they come in two kinds, circular ones and straight ones. And the idea is it's a resistive material, and you put 0 volts at one end and VDD, or your volt supply at the other end, and you measure you tap off in the middle somewhere, and that tells you where you are on the resistor. So that's what's used on most servos. And it has a problem that it's a mechanical thing with one surface rubbing over another, and it wears out, it gets dirt and grit in it. The rotary ones are better because they're enclosed. The linear ones have a problem. Because of this output shaft sliding up and down, it's hard to seal them. Like with the rotary one, it's sealed inside a casing. But with the linear, they're open. And so you get dust and grime and grit in there. That gets under the wipers, and they get noisy and jittery, and you just got to replace them. Or can't clean them out. And also the gears are open to the air, because again, putting the casing around this big long servo, you could do it, but there's difficulty. So typically they're always open to the air, and open therefore to grit getting in the gears, grit getting into the potentiometer. So what's happened with rotary servos is they've been on many servos you can buy now. They use this Hall sensor I mentioned about, that's used in Nick's little tiny servos, used in the half-gram servo. A Hall sensor which can sense magnetic field. Now there's nothing rubbing, so you can pick up the position of the servo with no rubbing parts. The problem is, how do you do that with a linear servo? Because you might think, oh, well, I just put a long magnet underneath the servo and a Hall sensor to pick up the magnetic. Well, it doesn't work. I don't sure I want to get into the reasons why. Well, at least it could work, but doesn't work very well. It's extremely non-linear. And getting that magnetic field the way you want it is quite difficult. So I looked at this, and in 2009, I invented a new servo, and I actually built one, and it worked just fine, but it was a kludgy thing with bits of 64th ply and carbon rods around. And making it wasn't just a simple replacement on a standard servo. And so it sort of sat on the shelf all these years, and then I thought, hey, with 3D printing I could print up the necessary pieces for a servo and get this thing built properly. And so that's what I've done. And so how does it work? And I'm not sure how much detail to get into here. What you ideally want is, the idea behind the whole thing is this runner that goes up and down. What I'll do is I'll create a magnetic field in here, so that, and I'll stick the Hall sensor onto the runner. So I'll make the Hall sensor travel up and down with the follower. And what it needs to see is a magnetic field that rotates, right? So when it's up this end, it may be seeing some North Pole, and as it moves down, it wants to see that magnetic field rotate until it gets to the other end and maybe sees the South Pole. Well, you don't actually want to go that far, but you get what I'm talking about. You want this thing to rotate so that the strength of the magnetic field perpendicular to the Hall sensor gets less and less and less till it's zero in the middle, and then gets more and more in the opposite direction as you go to the other end. So how do you make a helical magnetic field? Seems like a problem. You could come up with all sorts of things. Well, it turns out you can do it. This thing called, somebody throw an orange at me if this is too detailed. Matt? He told me not to get into too much detail. I'll go as fast as I can. There's this thing called a Hallback array. A Hallback array is a series of magnets side by side. The first one has north pointing up, the next one to the left, next one down, the next one to the right, and so on around as you go along. And so the magnetic field you get out of this looks like this. You get no magnetic field, virtually no magnetic field underneath, and you get all this magnetic field up, which is very well behaved up top. So, we're not there yet. If you take this, yes, it might be worthwhile. Here's 3 of those magnets. There's a north up, a sideways, and a north down. And this is the magnetic field above it. If you run a Hall sensor along quite close to this, here you'll be seeing north pointing up. In the middle, it's horizontal, and at the end, it's down. The trouble is, you've got to be about as far away from this as this length, the same sort of proportion, and that all makes the thing too big. But the essential idea that when you're in this position on the Hallback array, you are getting north through south. So now, if you take that Hallback array and extend it in depth, that view I previously had is looking on the ends here. So I extend these strips of magnets now. So there's a whole strip of magnet with north on the top and a whole strip of magnet with south on the top and so on. I can then take my Hall sensor, and if I was to move it from the middle of one row of this to the middle of the other one, I would experience this, but that's almost no distance. I get the right effect. So instead, what we do is we run the Hall sensor from one end of one magnet obliquely to the other end of the other magnet. So now I can make this as long as I want it by changing the angle. So at this end now I'm seeing north up, I travel all the way along, I see south up. That's what I want. And if you look at the magnetic field along that line, it is actually a helix. So you can generate a helical magnetic field. So what I do is cut a strip out of this Hall array, this Hall back array. So there's a strip of the magnet, it's at a bit of an angle, okay? And run the Hall sensor up and down. So, question is, where do you get a Hallback array from? Well, this is a Hallback array. So a refrigerator magnet. And
how would the weight of this compare with a conventional potentiometer?
well, you only use a tiny piece of it. I'll show you. But if you take two, I don't know if you know this, you take two refrigerator magnets, and I try to slide one over the other, watch what happens. It goes in jumps. And those jumps are, there's a row in this one here, which is attracted to the row in the other one. And as I push it, it resists, and then it jumps to the next matching pair, right? So you can actually measure how far apart are the Hallback strips in this, and you can see them. Or you can take something like this is a magnetic veering sheet. If I stick that, you can see, you can actually see the magnetic field on the Hallback array, right? So these are about 1.5 to 2 millimeters, depending on where you get
Can you
your.
pass that around?
Sure.
It's kind of hard to see.
It is. There you go. You can actually see a magnetic field. Right.
Move that sheet around.
This solves the major shortcoming of the linear servos.
So this stuff is it's what do you call it? A ferrite powder in a plastic carrier. You know, it's very cheap. I bought a sheet of it this long and a foot wide for a few dollars, so I've got enough to make 15,000 servos. You know? Which I'm not going to make. So it's cheap. That's the point. It weight for the kind of size, to answer your question, the kind of size that you want for these sort of servos. The piece of this weighs 1.1 milligrams. Not a problem. Oh, sorry, I'm sorry. It's 1.1 milligrams per square millimeter. 33 milligrams is the piece needed for the servos. 33 milligrams. You can cut it with scissors, and some of the stuff you get has got an adhesive backing, so you can stick it on. But, oh, there's a picture of that array from BBC with it there. Anyway, copy of that. So I've caddied up this. This servo. It looks like pretty much like a conventional linear servo. You've got the motor in the back there, the gear train, and the threaded rod. There are two problems with this servo. One of them is that if the follower is allowed to rotate just a little bit, that'll introduce a big error in the measurement, because with the conventional linear servo, if the follower rotates, jiggles a little bit in its guides, a little bit, the distance it moves along the threaded rod is negligible. But we're talking about spiral magnetic fields here, and if you rotate the follower, you're rotating it in the magnetic field, and it'll be a big effect. So this thing has to be constrained to stay pretty straight. It can't wobble as it goes along.
Could maybe that possibly be canceled out by having two Hall sensors to oppose each other, sort of mounted opposing, so if it did rotate, it would sort of be a, I don't know, subtractive effect on the two sensors, so they could,
That's a good suggestion. And I'll have to think about that. Thank you. Yeah,
Sort
okay.
of like a differential
Differential,
amplifier.
yeah. That's a good thought.
Yeah.
That's more complexity too.
Yeah,
Hall
yeah.
sensors. Yeah.
But the mechanical complexity might be simpler mechanics.
Well, what I did was I put a follower, a rod along 2-3 millimeters away from the threaded rod, and the follower has this slot in it coming out that goes over this rod, and that seems to hold it just fine. The second problem is that you've got to get wires to this Hall sensor. Thank you. You've got to get wires to the Hall sensor, so you've got to have some wires coming out and going over to your electronics. In practice, this doesn't seem to be a big issue, but it is a consideration. I use 36 gauge silicon coated wire, multi-core, and that just seems to work fine. So here's a picture of an actual servo. Again, the motor's in the back and the gears here, threaded rod, and there's this slot in the follower running along a carbon rod, and it works. So let me see. There's a planer, an ancient plane here that I used as a test bed. See, just like this one's got the ailerons and the rudder connected. So there they are running up and down. Just like a regular servo. One last thing, I think it's last thing. The bit about grit getting into the gears, as I mentioned, putting a case around the whole thing is problematic because you need a slot for the follower to run in. But with this, it would be quite feasible, I haven't done this yet, to put a little case around this one gear pair, right? A little box around the end of this to protect this from dust and grit. Because as I said, with all these servos, get a bit of grit in the gears, it can jam them up. But here you could put a box just around the gears on the end there and have this open to the air, because now it doesn't care about bits of grit underneath. And that would seal it up just as well as a rotary. So, so
How did the weight of that one compare to, like
I
a standard
think that's
one?
a little over a gram. Yeah.
Similar.
Quite small. The last thing was this issue of having to get wires going to the Hall sensor. Here's a picture from my CAD system 15 years ago. I designed this configuration where you stick the Hall array on the follower and mount the Hall sensor static in the electronics. So this thing now slides this Hall sensor, this Hallback array along with the follower, and so now you've got no wires. But it does have this annoying thing that sticks out the end of the servo and this Hallback array poking in there, which is less than ideal, but would get rid of the wires. But I find the wires are not in practice a problem. So there you have it, a Hallback linear. Oh, the one thing I forgot to say is the standard way that people do use Hall sensors with a linear servo is to stick a magnet on the end of the threaded rod with a Hall sensor nearby, and then you count the turns of the threaded rod. And that's quite accurate, it's a very good way of doing it. The one big problem is when you turn this thing on, you don't know where the follower is. So the standard thing is you run it off the end, and that means you need a limit switch, or let it smash into the end and detect the current peak. But you've got to run it to the end to find out where the end is. Now you know where you are and you're moving incrementally. And that's the way a lot of industrial linear actuators are done. you know, in wide use, and you've just got to put up with this startup thing. Well, with this, there's no startup. You just turn it on and you know where you are. So there you have it.
Wait a minute. Talk about Robert Gio and your micro models.
Yes. Thank you, man.
That's kind of
I
important.
appreciate that.
Yes.
Yes, somebody we haven't mentioned here that I've heard is Robert Gill, who sadly left us 4 years ago, something like that. Robert was a remarkable character. He was not a technologist. He was a lovely guy, all who knew him. And he got into this. He was a sculptor. There's some amazing sculpting things. And for some reason he got interested in micro airplanes. And he developed techniques for building small scale models. And I was fortunate enough to spend time with him, and he taught me how to make these little models. And at the same time I was just developing the Rabbit receiver, a little tiny thing, and he got the second one that was ever made. And got it flying. He was the first guy to get it flying. And so he made planes like this one. So that's one of Robert's, the airframe. And
How many channels?
this one here is 3 channels, motor, elevator and rudder, thank you. At the same time there was this thread on RC groups called brushless motors in the milligram range. I don't know if you've seen that. And in that thread, somebody came up with a brilliant idea from making your own brushless motors, and so Robert made those, and so did I. And he came up with that plane. This is my favorite. Newport, full scale.
We should point out that Robert's planes all flew amazingly well.
They did. Yeah, he was brilliant. This has a one-phase homemade brushless motor.
You wouldn't dare fly over the grass, you'd never find it.
No. And this has pull control on the full flying vertical stab.
Is it proportional control?
Oh, absolutely. Yeah.
Joe, you got a challenge.
Yeah, Robert and I used to go back and forth.
What else? There's another
Make him
one. Oh, Robert did this one. Yeah.
Yeah.
This is Robert's.
Oh my.
Yeah,
This is an Ord Hume.
Yep.
I think that this guy in England built in his attic, and he had to take the roof off his house to get it out.
Where is it? I see a red dot now. Where's the red?
This again is This is 2 channels.
So Martin, we're hoping to have, after we kind of go grab our lunch and come back, show and tell.
Yeah.
And what I'm hoping is people will bring their planes out and display, and you may be able to, you know, have that open so that people can kind of come by, look but don't touch, and see those planes.
Well, I've got to show you just this last one, but I will do that.
Yes.
But while I'm here, and then I'll be done. Promise. Not sure I can.
Yeah. So we'll bring them in.
So those are 3 models from Robert. I learned from him, and then built a bunch more tiny ones. And this is my
You gotta hold it up.
pride and joy. Let me a second here.
I could see a teenage boy in class getting bored from flying.
Right. Yeah. This is a P-51, obviously. It's 8 channels. It has throttle, of course, rudder, elevator, ailerons, flaps, retracts,
Oh my.
operable navigation lights, and machine gun. I wonder if I should have charged it up, but let's see.
Does that use a 10 light poly?
Yes. No, 20.
20, okay.
20. Oh, wheels went up. So you've got, you can hardly see it. The control surfaces hardly move. It's a very sensitive to
Show
anything.
the wheels.
Wheels? Which is that? Yeah, there you go. There you go.
Oh my.
skill speed too.
On going up.
That's amazing.
Machine guns.
Machine guns.
Oh,
Look at that.
Speaker.
amazing.
So much
Anyway,
stuff on it.
You can't.
And what's the call up weight on that one?
this is 3 grams.
That's
It's a bit beefy.
About a
It
penny.
flies at the scale speed of Mach 3.
Got a registrate on, right?
Huh? Right, so that's it. Thank you.
Thank you.